Right, so in this video, I'm going to show you what are these possible problems will be put on the final exam for this semester. So the final exam totally has 120 minutes, and it is open book, open notes. So which means you may see a lot of problems in there, and they can be a little bit harder than the normal homework assignments. But all the problems are reasonable. I won't do anything that is going to be beyond the quiz problems and the homework assignments. But you have to do it on your own, right? Which means do not exchange notes, do not exchange your solutions with each other. 120 minutes, open book, open notes, do it on your own, and send me the picture or scanned PDF if you have a scanner by email. Okay, and let's take a look at the possible problems I will put on the final exam. So the first one you need to know is Capacitor Network. So it can be a little bit different from all these examples over here, but you need to know how to calculate the series capacitors in series and in parallel as well, and find out the overall capacitance at the two terminals of the network. Okay, this is the first one. It can be pretty simple. It's not really that challenging. And the second one, definitely all these ones, things like a low pass filter, high pass filter, but you need to convert the circuit into the 70s equivalent first before you do any further calculation. And there's one thing you need to know that because this parameter is the amplitude of the sound wave, and in LT-SPICE, if you have a 2, number 2 here, it doesn't mean it's a peak-to-peak is 2, right? So the number 2 over there means it is sine. The first parameter is the offset, right? So I put a 0 there, so it's going to swing around baseline, which is the 0 volts. And if I put a 1 here and 1K, so that's offset. This is amplitude. Amplitude. And this is frequency. So amplitude means, so that's the amplitude, right? If I put a 1 here, which means the peak to peak is going to be 2, not 1. Keep in mind, if you want to have a peak to peak voltage to be 2, you need to put a 1 here. Okay? If you have a 2 here, your peak to peak will be 4. Okay. So for this one, I have a 2 here for the amplitude, so the peak to peak voltage will be 4. And if you are just calculating the amplitude attenuation, you don't actually need to care about this a lot. You just use VI, put a VI here, and use VI for all these calculations, and finally substitute the VI using whatever amplitude over here. But when you are drawing the amplitude attenuation on your paper, you hand draw it, right? So you have to be very clear about what is amplitude is, right? So you can make it correct. So that's this one, and the third one will be a op-amp design. We have done this for a few times in the quizzes and also in the homework assignments and also in the midterm, I believe. So you need to understand how to design a multi-stage. Keep in mind. Let me write it down here. So I will save this. Page 2. Multi-stage op-amp. So it doesn't have to be, like whatever we use in the lab. You have the first stage, which is a regular amplifier, and the second stage, you got a, what is that called? The instrumentation amplifier, and the very last stage, you got a comparator. It's not like you have to use all these stages in the op-amp, because we are assuming that no DC offset. So this DC offset means it's a difference between the two terminals of the op-amp, and that undesired DC voltage is being amplified to the output. So you are getting a DC voltage drift, which is you don't need it, right? But you just want the exactly DC offset to be applied to your output voltage to lift the signal to a specific DC offset. But sometimes there are some undesired DC offset, which is a noise, and we are assuming no DC offset, the undesired DC offset voltage. So there's no noise drift at the output. And also we assume that it's a real-to-real amplification. So based on these given conditions, and you are supposed to design an amplifier within a certain bandwidth. For example, the noise from the outlet is 60 Hertz, right? So you want to remove this signal. That's the first thing you need to remove. And the second thing you want to remove is DC offset from the sensor. And one more thing is you need to care about the signal's frequency. We used to use 1 Hertz for the heartbeat, right? It won't be faster than like 2 Hertz. So feel free to use a 3 something Hertz to filter out all these signals higher than that frequency, right? So for example, if I change the frequency to something above 3.4, what kind of parameters you want to pick up? Right? Just tweak the parameters of the capacitor resistor to make it happen, make it work. So these are the things you need to think about when you are working on that design. So you definitely will have an op-amp problem in the exam. And anything else? Let me see. So the fourth one, it's a pretty regular problem, the PN junction thing, just a concept you need to know. For example, this one, right? And I'm not going to let you do a calculation like for these ones, because I don't think it's making too much sense right now. You just look at, because open book, open notes, you can definitely just find the equation on the book and do the calculation. It's just waste of time. And the definition is like this, right? The concept. So you want to make sure you understand what are these parameters and how the PN junction works as a diode. And you want to save the time, so it's better to do a review on these ones before the exam. So when you get the problem, you can directly get the answer really quickly, so you are not wasting your time. So that's the fourth one, and the fifth one, the diode termination, the terminal characteristics. So for example, the voltage drop for the diode is usually 0.6 or 0.7 volts. And if you connect the voltage and resistor to the circuit and you do a DC sweep, what output will look like, based on this kind of circuit. So definitely there will be one problem about the diode terminal characteristics, and you just, because this is compared to other contents in this course, it's way easier, I think. So just take a look at this. I'm sure you are able to make it work, but you need to spend a little bit of time on that to do a review. Okay. If you do not do it, it's gonna take some time for you to look up the answers during the exam, which I'm not sure if you really have enough time to get everything done, because I have 9 problems in the exam. Even though it's open book, open notes, if it takes a lot of time for you to look at watch the videos and find out the answers, this is time consuming. Okay. And next one, so there will be 2 problems about the NMOS and PMOS operation, VGS, VDS, IDS, and how to calculate VGS based on IDS. All these parameters being converted back and forth. These are the fundamental things you need to know in this class. And if you are going to take one advanced analog circuit in the future in graduate school, you'll learn more about that. But these ones you need to know. Because if you are taking, for example, microcontrollers in the future, there might be some switching circuit. You really need a transistor to build a switch in the circuit. So you won't need too much about this, but some fundamental things to design a simple circuit, or to be able to understand whatever other people why they are using that transistor in the circuit. So things like this are pretty fundamental, and you do need to know. And I have been making this very clear. There will be 1 or 2 problems for calculating all these ID, VGS, back and forth. All right, and current mirror as well. It's not, actually, you cannot change too much about the current mirror problems, and we just don't want to give you any problems which are not covered in the course. So as long as you know how to calculate the current in the current mirrors, you'll be fine. It's going to be super similar to this one. And the last one will be a differential pair. It can be this one, or it can be something like this. So if you have this gate being shorted to the ground, then this transistor will be in the trial region, which means the resistance will be low. And if you have an output over here, and if you draw a small signal model, so let me show you really quick on the paper. So for example, the PMOS, I think I have a lecture covering this. Whatever this one is being shorted to. So here's a V out. And if you draw the current mirror, if you draw the circuit equivalent circuit, because this is AC ground, and you have ROP. This is RON. And the thing is, this is entrailed, and all these resistors are in parallel, right? So which means you actually has, this is flowing up, and this is flowing down, and you get RON. Here's ground. RON, ROP, and also there is a 1 over GM P, which is because this guy is in the trial region. So these resistors are, so here's VO. Those resistors are in parallel, right? And this is way smaller than all these ones. So that's why these ones are actually not working at all. So this will dominate your the overall resistance. So which means if you have a transistor is entrailed in here or in here, the overall resistance will be way lower, which means AC gain will be lower. Because VO equals to, I, whatever the overall I here, flows through this 1 over GM. It's going to be I times 1 over GMP. And because this is small, right? So that's why the overall VO will be smaller. But however, if you have this one in saturation as well, right? So the small signal model looks like this. Here's still VO and RON, ROP. And the resistance, overall resistance will be RON in parallel with ROP. And RON and ROP are pretty close to each other, and they are both pretty large. So the parallel resistor will be something way larger than 1 over GM. So you are getting a pretty decent voltage gain, because the current times this large resistor will be a larger VO. So that's why we want to keep all these transistors being operated in the saturation region, because they are getting a larger RO, the resistance. You are thinking about why, why is this larger resistor? I just look at the curve. Let me show you. So the operation of the NMOS or PMOS, it looks like this, right? So that's VDS, that's IDS. And because here is a channel, right? And VDS, this is VDVS, and here's IDS. And the current flows through the channel, and the voltage drop across the channel, and it's considered as a resistance across the equivalent resistance over the channel. And if you look at here, and that's delta I, and that's delta V, you can see that the resistance is delta V over delta I. And you can see that actually this is not a huge number, because V over I looks, in this curve, it looks like something close to 1, right? But however, over here, I couldn't even draw it. Let's draw it in another way, so probably it's more clear. For example, that's probably the real case, right? So the super flat one is usually just in theory. And if you look at here, and that's delta I, that's delta V, and delta V over delta I is way larger than this one, right? So that's why when you operate your transistor in the saturation region, you are getting a larger resistance, which means a larger gain. But in the trial region, it's not. That's the difference between these two regions. Okay, be clear about this. And for the small signal model, there are two things. Okay, refer to the CMOS book by Dr. Baker. So on that book, you will find out all these calculations for the small signal models. If you don't know how to make it work, small signal model of the op-amp or the amplifiers, and try to understand why you are doing the small signal in that way, right? So you can read the small CMOS book by Dr. Baker, or and any other resource online tutorials, or my lectures and notes, whatever. So the purpose is just to understand what is this. Right? If you can understand that, whatever way you can make it work, doesn't matter. I don't care. So make sure you know how to do the small signal model, and you know how to find out the AC voltage gain for the differential pair, and you will be fine for the very last problem. If you want to look at how, where is that one? Yeah, something like this, right? So the small signal, how the AC voltage gain was derived from here. You can look at the CMOS book. It has the entire derivation process over there. And so this, be careful, okay? So this or this, there will be one of these ones. So which means this transistor can be, the gate will be shorted to the ground or being shorted over to here as a current mirror. So it's going to be a little bit different, but not too different. Okay, but you need to know how to derive the AC gain as the V out for either of these problems. So if you watch the video and you have been making notes over here, you can find out I just probably mentioned about 9 types of problems will be possibly put on the final exam, and which is true. So there will be 9 problems, and in 120 minutes. So it's going to be something around 15 minutes per problem. It can be less than 15 minutes. So you are supposed to get it done quickly, not just correctly. Okay, and make sure it's open book, open notes. You know that, and do not exchange your solutions with each other. Do it on your own. You can find answers on the internet. Can be from the CMOS book, from the textbook, or the videos and lectures of this course, wherever, right? If you whatever is helpful for you to get the exam done, which is fine. Okay. All right. If you have any questions, feel free to email me, and hopefully, and good luck for all of these final exams for all the courses you are taking this semester, and stay safe. Talk to you later.